Hi, Inge.
Hi, Peter.
Welcome to the podcast, Everyday Metallurgy. Today, we are going to talk about something that for many years has just been an annoying part for me. Because as a steel producer, I have only been focusing on the steel and then the slag just above it. I just wanted to get rid of it, to get down to my steel where the quality is. But you are an expert in slag chemistry. But before we really jump into it, I was preparing for this, and I read an introduction to slag chemistry by Ken Mills, and in that I found the new law that I will absolutely follow in my daily life, because it's the unofficial first law of high temperature. It says at high temperatures, everything reacts with everything else. But then comes the second law. It's even better. It says they react bloody quickly, and it gets exponentially worse as the temperature increase. That's the life of sintering. It's the life of everything in chemistry, where you run at high temperature, where your enemy or maybe your friend is equilibrium. uh, Under normal condition, under low temperatures where we live normally, we very rarely see equilibrium. But I think you are playing with equilibrium every day.
Yeah, more frequently, I guess.
Yeah,
I
yeah,
think for high temperature metallurgists, the kinetics are less important than the thermodynamics.
exactly. Inge, will you give an introduction to yourself, where you're from, and what you're doing in your daily life?
Okay. I'm Inge Bellemans. I'm a professor at Ghent University, and since January also part-time guest professor at TU Delft, where I'm sitting actually at the moment by
Mhm.
coincidence.
Yeah.
And I focus a lot on slags and slag properties and slag phenomena by experimental work and simulation work on different scales. So going from the reactor level or even process or plant level up to or down to molecular level. And we
Hmm.
try to predict how a slag will behave under different conditions.
Yeah. Uh, yeah. Let's dig into what is a slag. Can you start to define what that means? Uh,
I,
Not only being
I,
something nasty on the top of a melt.
I thought indeed that maybe your introduction was a bit negative, but indeed a slag, it doesn't really sound impressive. In Dutch, it even translates into slak, and that's the same word as a snail. So
Ah.
when you say I do high temperature research on slag, people in the Netherlands and Belgium, they always look very strangely, what, escargots or something like that. Uh, but for people who do know what a slag is, most of them or some of them then say, okay, it's a waste. It's what's left over.
Hmm.
You need it for the process, but then afterwards you shovel it away to have your real product.
Yeah.
Um, but for me, a slag is really a finely designed liquid. It's a chemical tool, a sort of partner in crime in thermodynamics for the production of the steel or the metal itself.
Hmm.
There's an old saying in steel making, look after the slag and the steel will look after itself. And I think you can really um, do that for all metals because all metals have slag. It's,
Hmm.
wherever you have a liquid metal, there will also be a liquid slag alongside of it. So,
Yeah. And especially that the word that it reacts with everything. Uh, Also, the ceramic you typically have in a furnace, and I remember one of the things I was told when I was working in the melt shop was, oh, if you have a slag with high acidity, you need a lining with high acidity, and otherwise, if you have it with high basicity, you need high basicity lining. I never really understood what that was about. Can you give an explanation? What does that mean?
Yes, so slag chemistry sort of has its own dialect, indeed.
Yeah.
And Viscosity, it's maybe people reflect on it and think it's like the pH in water or something like that, but it has nothing to do with that. It actually tells us how oxidic components will behave at high temperatures. So basic oxides typically have more of ionic bonding nature. So they have less of shared electrons between, for example, if you're talking about calcium oxide, there's less shared electrons between the calcium and the oxygen. Whereas on the acidic side, the typical example is silicium oxide. Those are typically have more covalent bonds. So the electrons are more shared in between the different ions. In essence, a slag is a molten oxide solution where reactions are continuously happening all the time. And this ionic model, this was established by Richardson, I think, in the 50s, 60s. So it's somewhat older.
Yeah, but still pretty new.
Okay, pretty new stuff.
Yeah,
but
compared to the age of steel.
Yeah, that's true. But I think the research on slags really started off. And so with this ionic model, he was able to link that some oxidic components were more network forming, such as silica, the typical acidic components, and others were more network breaking. Later on, basicity was introduced. It's typically it's a ratio of the weight percentages of calcia over silica. Sometimes you can also include magnesia and or alumina and other components. And a high basicity slag is rich in calcium oxide, and it's very chemically aggressive. And it will easily absorb the acidic oxides. So it will be very aggressive against an acidic refractory. Similarly, for a silicate-rich slag, a low basicity slag, it's more viscous. There's more network within the slag itself. They sometimes call it polymerized. I don't like that word because it gives the idea that the polymer network in the slag is present all the time. And these bonds are breaking dynamically. Everything is happening dynamically all the time. So it's a bit strange to talk about a polymer being formed where it can immediately break down a millisecond after that. So I prefer the phrasing network formation, but I might slip in polymer once or twice during my because it's so embedded in the slag, in the slag dialect, really.
Yeah.
And so you have the basic slags will not work in an acidic lining or vice versa, and BOFs, EAFs, typical steel making slags are basic slags, and they will work in a reactor lined with basic refractories such as magnesia based, dolomite based, and on the other hand, non-ferrous refractories or furnaces will rather use more silica-based linings because those slags are also more acidic. But there are some downsides to basicity, that it's completely weight percentage based. So it's very useful for people in the plant on the floor because you just have your masses and you just easily calculate the weight percentages. It's very straightforward. but it doesn't distinguish between different kinds of cations which do behave differently. And then there are also certain elements that have amphoteric behavior, like that's similar as in aqueous solutions where you have acids and bases.
Yeah.
And then amphoterics can choose which either one behavior they will adapt to a certain situation.
Yeah.
And in slags, you also have that's, for example, alumina. And so if there's a lot of network already present, it will behave like a network breaker, and the other way around.
Yeah. When I think of a slag, it's the purpose of it is to protect the steel against the atmosphere on one side, and to be in reaction with the steel, because you have the steel touching it, and very often you have a movement of the steel, so you are able to actively remove some of the impurities that is dissolved in the steel. Are there other purposes of a slag?
You already named the two most important ones, the refining and protection from air. Yeah, I think protection from air is really the most important one. If you wouldn't have a slag, the metal would just completely oxidize and naturally form a sort of slag again.
Yeah.
Other purposes are, for example, inclusion removal. So it's possible that you have solid oxides that form as a sort of during the process, and then if these would get stuck in the steel, the quality would be completely destroyed. So you can actually use the slag to accommodate for those solid oxide particles. These will actually sort of float within the slag, but you need a slag that's thermodynamically fit to accept them. So it really depends on the thermodynamics, whether, and again, the slag network, so not just the composition, but the actual structure of the slag, to be able to accept them. And then besides that, there's also thermal isolation. So it's not just chemical isolation, so that the air wouldn't be touching the metal, but also it's sort of an isolating blanket, so to speak.
To reduce the energy consumption.
Yes, and for certain processes, you even have foam formation, and this foam can, and this is specifically true for electric arc furnaces and steel production, this foam is required for your process, because otherwise your arc would actually just be heating up your water-cooled elements instead of heating up your furnace. Of course, there would be some heating up, but most of the energy would be actually gone through the cooling system.
Yeah. So the slag inclusions I know of typical in steel is manganese sulfide, aluminium oxide, silicium oxide. Could that be removed with a proper slag control?
For the oxides, yeah, for sure. For the manganese sulfide, there is also some sulfur, the solution possible in slags. So I would need to check to be sure. But I think it would also be possible for sure.
Yeah. There's the anecdote about the Titanic steel that was so brittle when it hit the North Sea due to the low temperature, that when it just touched the iceberg, it cracked. So that was the reason why it sank. Can you confirm, and do you know what the reason was for the brittlement of the steel?
If I remember correctly, that has to do with ductile to brittle transition temperatures, and it's essentially that the steel was not of a high enough quality, it was not refined enough. So essentially, the steel makers didn't do a good enough job, and maybe by using a good or a better slag system, they would have produced a better steel quality. But due to that bad steel quality that was used in the rivets of the where they connected the different steel plates, and because of this low quality, when they reached the lower temperatures, this ductile to brittle transition occurred, and the rivets completely became brittle. So any impact or any force actually just broke the rivets completely.
Yeah. I'll jump back to the slags.
Sure.
Yeah, when I was melting, we had sometime a slag that was noodles. It was not liquid, but then we added some secret elements to it, and it became liquid. And I bought the slag atlas to understand what is happening in these ternary phase diagram. Can you give an introduction to what it is you are doing when you are controlling the content of the slag, and how to control that it enters the right liquid or the right viscosity phase?
I think there are two elements there that are important. On the one hand, the liquidus, or the fully liquid system, where you're discussing a liquid slag with perhaps some solids in it. But besides that, and I think that's what you mean, the viscosity of the slag.
Yeah.
So that it actually flows enough. And that's directly linked to slag structure and the network formation. Maybe I can go, I can dive in a bit more on that topic. I have a slide for that. Okay. So in slags, silicate slags are typically based on this SiO4 4- tetrahedron. This is the essential building block of a silicate slag. Now, if you would combine several of these tetrahedrons, you have all sorts of different networks or constructions that you can form. But this is just the silicates. Now,
that was what you talked about before, that it creates the polymers.
Yes.
Yeah.
I prefer network, but indeed polymer sort of network. But this is all still just silicates. What happens if we if we add calcium oxide, for example, a typical network breaker? Another example would be magnesium oxide or something like that. You will see that these networks will break up and also free up some of the oxygen. If you then continue further and, for example, also add aluminium, the amphoteric behavior, so it can be a network former and a network breaker, then we also see, so this is, by the way, a 2D representation to keep it visible. So there's only 3 oxygens per silicium.
Okay. Yeah.
Yes, because previously there should be 4, but this is a 2D representation.
Yeah.
And for aluminium, you see it has a 3+ oxidation state. So when you connect it to 4O2- anions, there's actually too much of a negative charge, and some of the network breaking ions should go and charge balance that deficit.
Yeah.
And this is what is going on continuously in slags. Network breaking, network forming, because these calcium 2+ ions, they are more mobile. The silicium ions, the aluminium ions, when they are in the network, they are not that mobile. And you can also see that if you have more of this network, it sort of, for me at least, seems natural that a fluid made of more polymerized slag will flow more difficultly than one with only small parts and network.
So the addition of calcium, if I look at the phase diagram, the ternary phase diagram, it has a big slope down, a big hole where liquidus just drops. So the melting temperature goes down. Is that because of the breakup of the chain?
Yes. That has to do with that.
Yeah, so now I understand the phase diagrams.
Well, I can show you several phase diagrams that I also don't understand, and maybe nobody on Earth understands them, but maybe I will stop sharing my screen now.
Yeah, but yeah, I make calcium treatment, and the reason for doing that was that when you initially kill a steel, because you have a certain level of oxygen dissolved in the steel, and when you want to pour it and you purge it to the tundish and through the nozzle, temperature drops. And when temperature goes down, the solubility of oxygen also goes down. And when that happens, the oxygen looks for something to react with. And if there is aluminium in the melt, let's go for it. And when I was making steel, it was tool steel, I was spray forming, and the nozzle I had was only 6 millimeter. And when it started to clock, I made things like that. Nothing comes out of this. This is a fully clocked nozzle. But to avoid the clocking, the gluing of the aluminum oxide in the nozzle, we added calcium oxide, because calcium oxide, aluminum oxide had a eutectic melting temperature, I think it was something like 1400 degrees C, so way below our casting temperature. So we just brought it into liquid phase so it wouldn't stick. I think I understand the chemistry of at least some of it now.
Yeah. Okay.
Yeah.
I think for slag, there's more to it than just chemistry. For me, it really links to the structure, and from there, the structure to all of the different, or not most of the properties you can explain based on the structure. The composition on its own, it gives you a certain structure, and from there you can really translate it into practical properties that, for example, the viscosity is also important for the tapping of furnaces. You want it to be fast enough, so it's not like honey, but you also don't want it to be too fast. So there's like an operational window there, and all of these things, viscosity has an influence on quite a lot of phenomena in furnaces.
Yeah. If you in the steel industry look at the properties you need for a slag, if it's electrode melting and you put in electrodes, they are passing through the slag, or are they? Where is the power going? So is the slag conductive, or do you need the contact to the steel? I don't really understand how it works.
For steel making, there are two types of electric furnaces. So electric arc furnaces, where the electrodes are not submerged into the slag, and then submerged arc furnaces, where the slag indeed acts as really the power source, so to speak. The resistance of the slag heats up the system through joule heating. It's really by letting current go through there that you will heat up the slag, and this then heats up the rest of the system.
So it's the slag that is the heat transfer part of it. So you also have to control your conductivity of the slag.
The electrical conductivity, yes.
Yeah. And is that done with the control of free ions? Or is it done with the, what did you call it, the blowing it up and making longer distance between the atoms? The foaming.
The foaming, okay. I thought the blowing up was...
No, not that blowing up. The foam process. I could imagine when you make foam, you have longer distance between the atoms and therefore...
and the air will also...
resistivity.
The air will also isolate electrically.
Yeah, exactly.
So, and indeed, it's not in the foam that the magic is happening, but in the slag itself. And it's the cations, so the calcium 2+, for example, the magnesium 2+. It's the movement of those ions throughout the network. That is the ionic movement. That is the electrical movement throughout the slag, or at least in a basic slag. If you have slags with elements that can have multiple oxidation states, sounds very scientific, but for example, iron 2+, iron 3+, and almost all slags have that element with several oxidation states. Then if there's sufficient amount of both of these ions and they are close enough to one another in the slag, electrons can additionally hop. And this can really increase your electrical conductivity in total, and we actually call it also two separate contributions: ionic conductivity and electronic conductivity.
So that's how it works. Thank you. The slag itself, how thick is a typical layer in a melt furnace?
Depends on the system. Also, in the beginning of your process, for example, a BOF steel making process, a converter, in the beginning there is almost no slag. There's just the pig iron, then the oxygen is blown on it. There are, of course, some fluxes being added, but it's only after a couple of minutes that some slag starts to form, or maybe 1 minute. I'm not sure whether anyone knows this, but
nobody looks in.
Initially you're just oxidizing the pig iron, so it's a slag almost completely existing of iron oxide.
And then the activity of a slag, it's caused by the viscosity, I can assume. So what happens when you go to higher temperature or lower temperature? Is it also temperature dependent, or doesn't it matter where you are?
Temperature will definitely play a major role, and I think activity, I would describe it as how available a certain component is. So it's instead of a composition, for example. And it will be, you can link it again to slag structure, but it's more of a composition related something instead of a property or network related. So it's definitely temperature dependent, and we typically use thermochemical software like Factage or Thermocalc to predict these activities of the different components in the slag.
And physically, I could imagine to protect it from air. If it's dense and it's noodles, it doesn't protect, because the air can just pass through. But what if it becomes too liquid? Will it still protect even if it's as liquid as the steel itself?
I think density-wise, it will float on top. but again, it depends on the process.
Yeah.
Because they are more stagnant processes and also very turbulent processes. In steel making, you have the BOF, where oxygen is really blown. There's a lot of splashing. The intermixing of the slag and the metal, they're a more liquid or a less viscous slag will actually maybe be a positive point. In non-ferrous metallurgy, you have top submerged lance furnaces, which essentially also have a lance from the top where you blow oxygen into the system. So you might think, okay, for the process itself, a low viscosity is actually good because you have more mixing, faster refining, but then the refractory will degrade faster again.
Because it can eat.
Yes, it can literally eat away
make the slag zone. Very often you can see that the reason for changing a lining it's not wear, it's slag zone that just eats in the lining. Typically, you look at it and say, I have impurities of slag in my steel, but can you also look at it the other way and say, I have metal impurities in my slag?
Yes, that was the topic of my PhD. Metal losses in slags are a thing, especially for non-ferrous metallurgy, where the economic value of the metals of the metal losses is larger. But ecologically, it's also becoming much more important because the slags they should become more circular. I think when I started my PhD, most people were always saying slags, that's just waste. I see a trend that this is changing and that everyone is really trying to look at the slag to be reused afterwards as well. But for that, of course, there cannot be any metal in it anymore. Topic of my PhD was investigating why sometimes the copper metal droplets were attached to spinel particles, and they wouldn't settle all the way through. But this is a phenomenon that also occurs in steel industry, for example. And besides the attached droplets, you also have just entrained droplets or chemically dissolved metal as well. And so slag cleaning operations might become more important in the future.
How much is it? Is it 1%? Is it 10%? What level are we at? If it's in a copper slag, as you mentioned.
Depends again on the process. You have converting and smelting slags for copper production, and one is in equilibrium with copper matte, the other one is in equilibrium with copper metal, and so there's also differences there, but several percent is definitely possible.
That's a lot.
Yes. And so for more valuable metals, settling furnaces are already present in most plants, but for less valuable metals, and steel is one of them, people haven't really been looking in that yet.
Can you disclose some of the latest finding that has been in the slag chemistry development over the last years?
I think over the last years, more effort has been put on making the slag more circular by slag cleaning, but also trying to combine different slags to make it more useful for example, supplementary cementitious materials or for carbonization, where the slag reacts with CO2 into sort of a building material. Yes, it really sounds very good. Then besides that, also understanding the slag better is still something we're working on. A lot of work on slag chemistry has been done in the 50s and the 60s. And you have the slag atlas, but I don't know whether you noticed the date of the atlas was 1995. That's the latest edition.
Okay. Yeah.
So we're
Yeah.
thinking of giving it an update and revamping it,
Yeah.
and to also try and look at compositions or wider compositions, so that using scrap and non-ferrous metallurgy are also included more, because the systems that are mostly investigated in the Slag Atlas are for primary production based on ores, etc., which of course makes sense if you look at the timeline. But nowadays, using scrap becomes so important that the slags should also be adapted to being able to work with that scrap. But there's no data. So
yeah, because I could imagine that today with the possibility of simulating thermocalc, maybe even use AI or machine learning, there could be new ideas popping up on what could be done, changing the chemistry or doing something that we have never thought of before.
Yeah, for sure. In our lab, we're trying to investigate the slag properties experimentally and combining that also with atomic simulations, so molecular dynamic simulations, and then determine the slag properties from that. Because experimentally, it's the same as in the industrial furnaces. There's refractory interactions, sometimes limits in temperature, sometimes just limits in atmosphere, whereas in silico, so to speak, you don't have those boundary conditions. But we always check it with experiments as well. But machine learning can be very valuable, but first you need data for that. So we first want to produce more data, and then maybe we can also use machine learning or AI to obtain better structural property or composition temperature property models that are more useful for industry.
Yeah, I read an article about some that made trials on refining the steel, and they were able to adjust the level of boron in the steel through the slag activity. So there, I could imagine that all kind of impurities that you will see now going into more recycling. You'll add copper, you'll add boron, you'll add phosphorus, lithium, things that typically is not a part of steel chemistry, but it will enter the circularity chain if you could refine that instead of diluting it. I could see a great potential in the slag world if that was possible.
Yeah, for sure. And this is also a project we started recently to look at slag cleaning to obtain the various metals that are lost within the process, but maybe are recoverable afterwards.
Yeah. And if we jump to the end of life of the slag, I have seen slag being used in asphalt. I have seen it being used in cement. But what do you see will be the future of slag? Will end of life be in the asphalt? Typically, when we say put it in the asphalt, it's a place where you will never see it again. So absolutely not recyclable.
I hope that in the future slags become more recyclable, and that if you could tune the outputs of certain plants to the inputs of other plants, and maybe in between do a cleaning step or something like that, that one plant wouldn't need mined resources, but could use the otherwise waste of another plant. That's my hope.
Yeah, so a synergetic connection.
Yes, yeah. And I think there are actually several opportunities there, especially if you look at non-ferrous, ferrous industry combinations, or even by combining the end slags of two processes, you can sometimes optimize the properties so that it's more applicable for cementitious or as supplementary cementitious material. Because the best SCM is actually blast furnace slag, but with the green steel transition, blast furnace slag will normally become less available.
Yeah.
So, and in Europe, I think 99% of the blast furnace slag is recycled already as SCM. But we need a replacement for that now. Yeah. Or we should be thinking about replacing that kind of material with maybe a combination of other slags or something like that.
Yeah. To know the annual volume of slag, if we just look locally in Europe, compared to the level of iron or steel.
I have a slide for that.
Yeah.
These are some data points from Eurofair, so European Steel Association, and they also look at the slag production and use. Note the units, so it's in million metric tons.
Oh.
This is in Europe, the amount of slag that is produced. And this is only for steel and iron production. For non-ferrous metallurgy, you also have slags, but of course, this is of another dimension. If you compare,
this is the majority.
Steel, this is the majority. And they also look at how the slag can be used. So part of it is deposited, but some of it is also used as fertilizer in agriculture. Then there's also some cement, concrete, and mineral wool was also a new one that I discovered this year.
So isolation in houses.
Yes, and I think that's actually a quite harmless application, because the use of slags and the possible leachability of certain elements is always a thing. And I think if you can find applications where leaching is minimized, I think that's ideal. And with mineral wool, that would be, I think, or for isolation, that seems like a good option. Let's just put it that way.
Yeah.
I will stop sharing. Okay.
Yeah. Yeah, I have a last question going back to the technical part of the slag. Slag is also used as a refining agent, and in the tool steel world, there's the electroslag remelting process, where you have a billet and you drop melt it through an artificial slag that contains fluorides. And then the steel runs through all the impurities. They are dissolved by the slag, and what is coming out at the bottom and being solidified is ultra pure clean steel. So that it's steel that you can mirror polish because there are no inclusions in it, or almost no inclusions. Can you share a little about those kind of slags?
I actually don't know that much about those slags, but it's a very similar process as what is actually happening in a converter. There, in a steelmaking converter, you have the oxygen blowing lens, which I already mentioned, and the pig iron droplets are dispersed into the slag. And it's the actual refinement is not happening from, or there is some refinement happening from the oxygen going onto the metal bath, but the metal droplets and being inside of the slag phase, that's where the actual refinement is taking place. Because of the amount of slag surrounding those tiny droplets.
Yeah.
And I think in electromelt refining or electroslag refining, this is a very similar situation where at the top you melt the impure metal, and then during the descent, actually with the synthetic slag, which probably, if you say it contains fluorides, it has a very, it's not viscous at all. It will be very fluid. And so that also means that it has not that much network, and hence the reactivity and all of the kinetics, all of the diffusion, everything happens very fast. And so during the descent, the thermodynamics can completely be established. And if you choose the composition of the slag in equilibrium with your final metal in a good way, you can really refine that steel up to a very nice quality. And in the end, I guess at the bottom there will be some water cooling so that you can also solidify your metal again.
Yes, it's typically in a copper cylinder that is water cooled. So it's also kind of forced solidified on the walls and at the bottom. So you know something about it.
Okay.
Inge, if people are interested in learning more about both the slag, the refining of it, and refining of steel, where should they go? Are there conferences? Are there books other than the Slag Atlas they should read?
There are conferences. There's a conference on molten slags, fluxes, and salts. I think last time it was in Brisbane in 2024, and next time it will be in Toronto. I think 2027. I'm not sure.
Okay.
But it's molten, so it's an unmistakable name. And I would say that is the molten slag conference. There's also a Euro slag conference focusing more on what happens with the slag afterwards, being the applications, etc. And maybe we're a bit late now, but that's in May or June in Luleå in Finland this year. Oh, Sweden, sorry. Geographical mistake.
Perfect. Thank you very much. I learned a lot. I had a reimagination on what happened. So my simple version of just looking at the phase diagram and seeing the eutectic liquidus solidus points dropping has been dramatically changed with the network creation and the polymer creation of the silicon oxide.
It's not that I say that you cannot use the word, but it gives the impression that it's a fixed network, and that's not the case. No. It's a very dynamic system, and it's and it controls almost everything in a furnace.
Yeah. So thank you very much. I really enjoyed it, and I hope you also got some reflections.
That's very nice. Thank you.
Yeah, thank you.